Hey everyone, how goes it? And welcome back to Computer Science 552 Game Development. Today, we're going to continue to discuss game development. In the past lectures, we focused on the concepts and the roles related to game production. We began discussing game development in a previous lecture. Today, we continue this discussion. We turn our attention again to the role of the programmer. We focus on the element related to creating software in order to make a game. We continue again discussing game programming. In a previous lecture, we discussed some of the values and concepts related to software engineering. Creating a video game is an exercise in software engineering. Software development processes help to plan, manage the tasks required in order to create software. A software pattern is a general, reusable solution to a commonly occurring problem within the given context of software design. Some common software pattern categories are structure, behavior, creator, and concurrency patterns. The game loop pattern helps to organize games' behaviors into common occurrences. Each game loop iteration progresses the game. The event step helps gather information about occurrences that happen since the last game loop iteration and applying necessary actions that are related to the event. These can be related to user input, collision detection, message handling. These are all common events. The update step modifies the data periodically based on the previous events and previous data. Moving the player, destroying an asteroid, or collecting a coin are tasks that are commonly performed during the update step. Finally, draw displays the results of this update. There are steps that exist outside the game loop that we must consider. The initialization step is when all the data for the game is created and set to default values. This occurs before the game loop. Similarly, the finalization step is when all the data is deallocated from memory, and this happens after the game loop. For argument's sake, the initialization and finalization step are not part of the loop, but they are considered in the game loop pattern. However, when we decide to create games that involve more features, we need to consider more sophisticated structures and patterns. More game features require more sophisticated structural organization. Video game software or game software is the entire collection of the game-specific code, libraries, systems, and engines that compose a video game. The game system is the code which runs or drives the game. It is in charge of calling the functions that are related to the game loop pattern. It contains software libraries that are used to write the game-specific code. It's also considered to be separate from the game-specific code itself. A game engine provides many of the features common in modern games. We do not need a game engine to make a game, but as a developer, it does speed up the process. Game-specific code is the software specifically developed to create a game. Again, it is separate from the game system, and typically it uses provided features and programming interfaces that were provided by the game system. Game engine is a software framework for developing games, and it includes the necessary software libraries and supporting programs. In many cases, it contains the graphic library, the physics engine, input manager, audio managers, message passing capabilities, and etc. As mentioned, game engines are not required for making games, but it can help speed up the process. In many cases, the game system can be considered the game engine. Game software structures can be viewed in a slightly different way than most typical object-oriented design software. As mentioned, the Entity Component System (ECS) puts more stress on composition over inheritance. It focuses on not what it is, but what it does. The component pattern allows a single thing or behavior to span multiple domains without requiring specific relationships to each. It is considered to be a decoupling pattern, and it has much in common with the composite pattern, where programming objects are composed of other programming objects. Component-based development emphasizes the separation of specific functionality with respect to the wide-ranging functionality available throughout a system. Components for games are classes of behaviors. We create classes of behaviors instead of classes of things. This is opposed to hard coding functions or methods within one large monolithic class. This means we would write everything in one programming method or function. The code for components are based on the game loop pattern. We typically have separate functions for initialization, updates, events, draw, and finalization. Typically, within a game engine, there is a component programming interface from which all components must either inherit or implement. Game objects are the abstract nouns in a game. Every thing in a game is a game object. Every object, player, enemy, rock, any of that is a game object. Game objects are considered to be the entities in relation to the entity component design. We can consider them to be simple containers for components. And in many cases, game objects can be considered to be components themselves. Generally, classes are not specifically created for different game objects. There is no specific class written for player, for enemy, or for exploding barrel. Game engines commonly have a data type game object that is used to then extend to specific kinds of game objects. Game objects are differentiated based on what behaviors they perform. The difference is not based on a data type, but on how it behaves. By using this structure, this allows for functionality to be abstracted. Many game objects perform the same actions, so they share the same components. We can see both player and enemy can move and draw. We consider writing one class move and another class draw and simply add those to the player and enemy game objects. The component's attributes may be different in each instance, but the components do the same action. For instance, a player's speed and an enemy's speed may be different, but they're still moving the same way. From a functional standpoint, they do the same thing, but they just have different values. Game objects may also swap in and out different behaviors. This kind of flexibility allows it to be decoupled and allows some game objects to either gain or lose abilities. Writing game code requires understanding what are the nouns, the things, and what are the verbs, actions, and behaviors that are inside the game. One way we can start doing this is by noticing the nouns and the verbs while reading the game design document. By categorizing nouns and verbs, these assist in writing the technical design document. Game code is generally composed of game objects, the nouns, and components, the verbs, actions, and behaviors. This becomes the foundational structure of a game. The game objects and their components are smaller parts of the overall game system. In game design, we discussed how all games are systems. Commonly, the game system is the code which runs or drives the game. Again, it's in charge of calling the functions related to the game loop pattern. These function calls can be considered event messages. They are sent to each game object and then delegated to each component. Being a little more specific still, the game system also is composed of libraries and other systems such as programming interfaces. Game systems provide the game developer features that are commonly found in games, and for the most part, the game engine can be considered the game system. The big overall structure is, the game system is composed of collections of components which we call game objects. Game objects are composed of behaviors that we call components. The game system follows the game loop pattern. It initializes each game object and each component within. It handles the events for each game object and each component within. It updates each game object for each component within. It draws each game object for each component within, and it finalizes each game object and for each component within. To better understand this, let's look at a few more examples. We're going to create a simple space shooter game where the player defends the galaxy from interlopers while traveling through an asteroid field. Now, let's gather some requirements. The player must be able to control a spaceship by rotating it and moving it both forward and backwards. The player must be able to fire a laser in the direction that they are facing. Periodically, the game will spawn enemies. Enemies can either be asteroids or space interlopers. Asteroids have a fixed direction and speed in which they will travel. Space interlopers are more intelligent and they will track the player and fire lasers at them. Collision detection between lasers, asteroids, space interlopers, and the player must all be detected. When a player's laser collides with either an asteroid or a space interloper, then the enemy's health is reduced. When the player collides with either an asteroid, space interloper, or an enemy's laser, then their health is reduced. Destroying a space interloper is worth more points than destroying an asteroid. When the player's health is reduced to 0, then the game is over. The game has stages which increase in difficulty as they progress. The current build will have 5 stages. Each stage will have the same time limit, but the types and the amount of enemies that spawn will increase as they progress. The player must survive as long as possible while earning as many points as possible. When either the player survives through all 5 stages or when they perish, their high score will be recorded. Once again, let's start identifying the game object by identifying the nouns and the requirements. We notice a few game objects immediately, like player, laser, interloper, and asteroid. While we do not see it explicitly written, there is another game object that works like a referee, official, or point keeper, which we will call the scene manager. Having one game object act as an official inside the game can help us organize overall rules and goals for the game. Many times we can identify this game object when we notice that the game needs information managed, like points, timers, and etc. We also notice that the scene manager is also related to the stages, or the other scenes throughout the game. Now we can start identifying the actions related to each one of the game objects. Starting with the player, we first notice that the actions related to user input. Moving the player and firing a laser are actions that must happen based on inputs by the player. We also notice that we have a transformation component, which contains all the location, rotation, and scale data. A spaceship is mentioned, and we can think of this as being a 2D image, which we'll call a sprite. We also notice that it mentions collision detection, and we're going to use a simple geometry called a collider to detect collision among the different objects. Collision detection is important, but we need something that handles the collision response. These events are sometimes very specific to the game object, and so we need to write them specifically. In our case, we need to handle collisions between the player versus an asteroid, an interloper, and a laser uniquely and differently. These will be different than the collision responses that are handled inside the asteroid, the interloper, or the laser. We will discuss this in more detail, and there is a critical difference between collision detection and collision response. We also have a health system which will work alongside the player's collision response system. Putting it together, we can see the design for the player. From the user input, we can move and spin the player, which is handled by the translate and rotate functions provided by the transformation component. The sprite is drawn at the location provided by the transformation component, and the collider also uses the same position for its location. The collider's messages are processed by the player collision component, which handles some of the collision by using the provided reduce health function in the health system. We also notice that there are 2 exterior dependencies that we must address. Firing a laser requires it to create a laser game object. Notifying the scene manager that the player has been destroyed requires a scene manager game object. We need both of these to complete the player system, so let's move on to some other game objects. Before moving to the next game object, we can consider the design to look like this. The main difference between the relationship between the collider and the player collision components. We notice that this time, a dash line is connecting one ball joint to another. From this diagram, we can interpret this as being a less strict requirement, meaning that the collider does not specifically require anything to handle the collision, but instead we consider this to be the same as the game object or the game system requiring the component to be implemented. Moving to another game object, we first notice that the laser needs position rotation data, so we already know that it has a transformation component that handles all this. We also need to draw the laser using a sprite. Firing the laser requires the laser to move. The laser motion component handles the movement of the laser and also the collision responses. We could have separated this into two different components, but we decided to integrate them both together as it would simplify the design. Again, there are many different ways to design these systems to work, and some are better than others. As long as it works well enough, then it's not really a problem. This is another example of where the collision responses are handled in a different behavior than the collision detection. This is again handled by the collider component to detect the collision, while it's handled differently elsewhere. We can now see the laser game object and its assembled components. One major detail is the connector outside of the game object that says instantiates. Instantiating is the concept of creating a new instance of a game object, and we could think of this functionality as being provided by the game object itself. When we instantiate a new instance of a game object in our world, it is created along with all of its components. While this functionality is assumed to be provided by all game objects, in our design, we only indicate them when necessary. Connecting together the two game objects, we can now see how they work. From the user input component, the player fires a laser, which instantiates a new instance of a game object called laser. Moving on to the next dependency, we can see that the scene manager's code could be all simplified into one single component. While much of the functionality could be separated into various interconnecting components, it may at the same time be overcomplicating the design and slowing down the game loop. This is a trade-off between writing a few large components versus writing many smaller components. Writing a few large components can be much faster within the game loop, but it limits flexibility when adding and modifying features. Writing smaller interconnected components allow for more flexibility and allow for more code sharing. But it can also become too abstract, overly complicated, and also slow. Finding a balance much like this is important. Always ask, what are the troubles and are they worth the time? The functionality related to the scene manager typically deals with constitutive rules like point scoring and timers, but they also integrate goals by implementing the win and loss conditions. In essence, they manage the rules of the game, or at least a smaller part of it. Adding the scene manager to our design, we can see how the health system will notify the scene manager that the player was destroyed. The scene manager game object is fairly simple, and we do notice that it has a dependency as well. We need to be able to create instances of these enemy game objects, the asteroid and the interloper. So now we take a look at the actions related to the asteroid. Once again, we see that a transformation contains the position rotation scale data. The collider handles the collision detection, and the sprite of the asteroid is used to draw the game object. We also note that it does have some unique components such as aster movement, which incorporates both the motion actions along with handling collisions. Interesting to note that much of this is very similar to the laser game object, except it has a health system, which is affected by the collision response. Now we do the same for the space interloper. This is slightly more advanced than the asteroid, but it still shares many of the same components. It is interesting to note that track player component is used in the same way as user input. This is also where more sophisticated AI could be integrated into the enemies. Now putting them all together, we can see the design for the game. We can see all of the game objects along with their components and how they are interconnected. This nearly feels like the entire design, except it seems to be missing a couple of features. We notice that there are stages which increase the game's difficulty. We do not seem to have this concept in our component design, but we have mentioned that the scene manager can be used to handle something like this. Also, when we consider most modern games, we have to wonder, where are the menus? Where are the graphical user interfaces? This has yet to be mentioned, and both of these require an understanding of another level of organization. Game objects can be further organized into scenes. We can think of these as being different sections or environments of the game, different levels, different rooms, different dungeons, etc., which would all contain only these game objects and these components. Scenes help separate and organize different sections, stages, levels of the game. When a scene is loaded, only the game objects and their components associated with them are loaded together. More can be loaded and unloaded as needed, and also scenes can help reduce load time by separating it out. Scenes can be used to further structure a game. The scene manager helps enforce the constitutive and operational rules for the game. Many times, it does focus on the overall goals, win and loss conditions of a game. Scenes can be used to further structure the overall game. Again, different scenes may have different interaction, rules, and objectives. A scene manager can be used to implement the goals, rules related to specific scenes. The scene manager can be considered a special kind of game object that contains all the relevant scene information, such as points earned. The scene manager contains components which implement the rules and objectives, such as time limits and win and loss conditions. The scene manager also assists in transitioning from one scene to another. Finally, scenes can be organized into a state machine. State machines can be used to outline the flow of scenes for a game. Boxes are the scenes, such as menus, levels that represent a game's state. Arrows represent the action required to move from one scene to another. Start and exit are special states indicating where we start and we exit. In the technical design document, state machines representing the scenes are very useful for showing the flow and progression of a game. Arguably, this can also be very good to have in a game design document as well. Now, this is in addition to the component diagrams. The scene managers can be responsible for creating these transitions and implementing the scene state machine. This is in addition to the component diagrams showing the inner workings of a game object and the components within a scene. For our game, we can include this in our technical design document. As mentioned, within the technical design document, it is useful to have state machines representing the scenes. Scenes should be clearly indicated. The name of the scene and the internal scene name. Objectives, the rules and the goals for the scene. Other comments related to this can be added for better clarification about the rules and the objectives of each scene. List of all the outgoing transitions, like for example, to this scene when this condition happens. A list of all the game objects within the scene. Game object and component diagrams for each scene. Including rough sketches of these user interfaces for the menus can also be useful in finalizing the design. We can start seeing an example of these details for our scenes. Here's an example of the main menu scene, which also includes the component diagram. We notice that each one of the game objects within the system with their associated components. More details regarding each game object and the associated components are within the provided game design document. Now, we can start to see an example of Level 1. We notice that it contains the component diagram mentioned earlier. Skipping ahead a few scenes, we notice that Level 5 appears to have the same component diagram. In fact, most of these seem to be about the same except for the transitions. The amount of time that the player has to survive, and the density of enemies. We notice that this is the same structure as Scene 2 through Scene 6. All of these are variable properties that can be set in the Scene Manager component for specific levels. Now, by creating this one scene, we can actually replicate it and adjust some of the Scene Manager properties to increase its difficulty. Now that we have a better understanding of this, let's take a look at another example. This time, we're going to focus on creating another type of game called a platformer. The main goal of these types of games is going from point A to point B as quickly as possible while earning as many points as possible. Platformers were one of the most popular game genres in the late 80s through the 90s. While not as popular today, it remains a strong game genre for those interested in perilous parkour play. Now, here are some requirements for the game that we want to create. The player must be able to run and jump around a side-scrolling 2D environment. Forces such as gravity must affect the player when either they jump or fall off a platform. The player can only jump as long as they're touching a ground surface. The player's goal is to reach the end of the level and earn as many points as possible. The player collects coins and defeats enemies to earn points. The player also has a limited amount of time to reach the end of the level. The time left over earns the player points when they reach the end of the goal. There are 5 levels and are rich with platforms, pitfalls, and enemies as they progress linearly. When the player collides with an enemy, they lose health. Once the player's health reaches 0, then the game is over. The player can attack an enemy by throwing a hammer, which is also affected by gravity. Now, we can identify each one of the game objects by noticing their nouns. We can see there is a player, coins, enemies, the ground representing platforms, and hazards representing pitfalls. We also notice that there is a goal game object which the player is attempting to reach. We notice that there is a limited amount of time and is highlighted as the scene manager. We now understand that this game object, which represents the referee or game official, is typically used to handle many of the rules and data that is important to a scene. We also know that this game object will be in charge of transitioning from one scene to another. We also notice another game object called camera, which is associated with side-scrolling 2D environments. In order to simulate the character moving around an environment, we can have the camera game object follow the player around. Using a camera to follow a player is a very common way to draw a scene. We now focus on the player game object, and we do this by noticing the verbs. Once again, we need a sprite to draw it. User input allows us to capture the controls related to running and jumping. The transformation component holds all the data related to position, rotation, and scale. The collider detects collision, and the health system keeps track of the player's health. We also notice a special highlighted component called a rigid body. One major detail to note is this type of game requires more sophisticated physics in terms of both detection and response. A rigid body is a common type of component that applies classical mechanics to a game object. Keeping in mind that classical mechanics is a branch of physics concerned with the study of bodies in motion, which are affected by forces. Remembering Newton's laws, and especially force is equal to mass times acceleration, this is critical in understanding this. This component provides a means to assign mass to game objects and also apply forces such as gravity or other external forces on them. It assumes that the object does not deform and applies the forces based on a rigid body. While this may appear to be a little complicated, we recognize that this is just another kind of component that falls within the game loop pattern. In terms of design, we are not concerned with the details about how the forces are applied, just so long as they are. Putting together the components inside the player, we can start to notice some of the differences when we use a rigid body. First, we notice that the user input to run needs a connection to the rigid body's velocity. We can assume that the user input will be affected by the velocity when the player is moving. We also notice that the jump requires the function adding force. We can assume when the player presses jump that a force will be added in the up direction, thus simulating a jump. We also notice that the rigid body receives collision messages as the rigid body and the collider work together to detect collision and impart the forces based on the response. The rigid body then connects to the transformation component, which allows the forces and the physics to decide the position of the rigid body. We should also note that the rigid body may also affect the rotation, but in our example we are only going to focus on it changing position of the player game object. This game object has some external dependencies, and we're going to focus on the projectile as it has some similar concepts. We can start seeing the components regarding the projectiles. We recognize that there are some very common components such as sprite, collider, and transformation. All of these once again are needed to draw, detect collision, and contain the location data respectively. We also notice that we have a rigid body as a part of this as well. As the projectile is being pulled down by gravity, it needs to have forces applied to it. In fact, throwing the projectile is applying a force to it, and so this projectile requires this component as well. Adding this new game object to our design, we could see how the player instantiates a new instance of the projectile. We also notice that there is a message being delegated to add force. We assume at the time the projectile is instantiated that a force is immediately applied to it, thus simulating the act of throwing an object. This could have been written as a separate connector, but we decided to combine it for simplicity's sake. Before we move to the scene manager, there is another game object that is related to the player that is very important to discuss. Going back to the requirements, we are going to focus on the camera game object. In other games, the player could freely move around the bounds of the environment. The environments were assumed to be small, never moved, in the exact size of our window frame. However, in this type of game, the player moves around a much larger space, which cannot be reasonably viewed all at once. We must limit the viewing space for the user and focus on the player's location by zooming in to where the player is at, and this is within the larger environment. In order to do so, we use the concept of a camera game object. This will only draw the game objects within a specific window frame so that we can create much larger levels than our windows. The camera game object, of course, requires a camera component, which handles drawing the current scene. The component contains all the data related to the size of the window frame and even more details such as projection types, render layers, and field of view degrees. We also notice that the camera geo has a transformation component which will contain its location and rotation data. Yet, there is something special that we need to notice about this particular transformation. In our game, the camera must always follow the player. We already know that the player has a transformation component which contains the position data. In fact, this transformation component depends on the player to follow. This is a common relationship that's found in many games. Most game engines, or most game systems, assume that every game object has a transformation component. Transformation components hold all the location, rotation, and scale data that is related to a game object. Its position in X, Y, and Z, its rotation in pitch, yaw, and roll, and its scale in X, Y, and Z scale. We can think of this as being the same as the move component discussed in previous examples. More technically, it transforms the local coordinates of a game object into the world coordinates of our game. It also handles the calculation related to the transformation functions. Translate is a function that moves a game object. Rotate is a function that rotates a game object, and scale is a function that changes the scale of the game object. With this in mind, game objects can be further organized into hierarchies. This is a tree structure which generally links together the transformation components of a parent game object to affect the transformation component of a child game object. This is like any other tree structure in computing where this contains no cycles, and it commonly is used to create a hierarchical system. The topmost game object, or the parent's hierarchy, is the global or the world coordinates. Any child game object has local coordinates, which transforms the data that is relative to the parents. If the parent game object translates, rotates, or scales, then so will all of its children. We can also clean up this design slightly by enclosing one game object within another. The enclosing game object is the parent, and the enclosed game object are the children. We remember that game objects are components, and we can have components composed of other components. With this in mind, we are aware of the enclosing transformation will modify the enclosed transformation, and we could do this without adding any additional lines. Adding the camera game object to our design, we can start seeing the parent and child relationship between the camera and the player. Whenever the player moves, thus their position changes, it will change the position of the camera. This simulates the actions of the camera following the player around the environment. We also notice that the camera does not have a rigid body component. We keep in mind that only objects that need to be affected by forces directly require a rigid body. The camera does not need to be affected by forces like gravity and only needs to follow the player. We can continue to notice this concept when we are creating the ground, hazard, goal, and coin game objects. They need to be able to detect collision, which is why they have colliders, but they don't need to be affected by forces. Collision detection is different from collision response. Collision detection is handled by colliders, and the responses are handled by other scripts, which may include rigid bodies. One key tip is rigid bodies are only needed when forces need to be applied, and gravity is always a good place to start. Now, putting them all together, we can see the rough design for this game, and we can see the game objects along with their components and how they interconnect. The complexity of this type of game is much larger in scale than the previous ones discussed. In fact, for sake of space, some game objects needed to be combined together, such as coin and goal, but in the full game design and technical design documents, these would be fully displayed. We always have to keep in mind that the purpose of this is for communicating these ideas. We're not making designs, we're making designs for games. Now we see this and we can start putting it together with our idea of scenes inside the game. We now can organize the game into our scenes representing the menus and the levels of our game. We see there are 5 levels and it progresses linearly, and we also notice the detail not mentioned in the requirements. Some levels have a secret skip that allows the game to be beaten much more quickly. These are great details to put in the designs in the case that the game may be non-linear and may feature levels or branches or even loops. To finally sum everything up, creating a video game is an exercise in software engineering. Recognizing common software patterns is critical to quickly developing solutions. The game loop pattern is a behavior pattern facilitated by the game system. Thus it calls initialization, events, update, draw, finalization. Game systems are structured based on the game object which contains components. This is based on the entity component system and the component-based pattern for games. Game objects are simple containers for behaviors we call components. Components are classes of behaviors that represent the action the game object can perform. We further organize game objects into structures called scenes that can be represented by a state machine. All of this information is found in the game design and technical design documents. Now that you've seen how a game is designed, it's time to move forward in learning the skills and how to develop the game. In the next series of lectures, we're going to focus on features and functionality that is common for game engines and how to create assets to work with them. Until then, I'll see you next time.